So okay, welcome back to this discussion of the covariance of two random variables h and m. So we've said we have this probability distribution where we have all the people on this planet, and we have two random variables h and m which ascribe to each person their height in meters and their mass in kilograms respectively. And basically what we said is we can make a joint, we can consider this a joint or a bivariate random variable where you're ascribing an ordered pair to each person, and then we can let this subspace of R2 assume the probability mass function from over here. So if there is, if you have a point in here which indeed does have a person who has those measurements, then it will inherit that probability basically. So if you take any point, you need to work out how many people in here have those measurements, what's the probability of picking that set of people, and that's the probability of that ordered pair coming up. So basically what we're now trying to understand is what is this covariance of these two random variables. Well, we have a formula, and I've said that in some sense it's going to measure how positively correlated or negatively correlated the two are. And indeed covariance will be positive if they're positively correlated, and negative if they're negatively correlated. There is a better measurement of correlation, which is correlation, but it's extremely related to covariance. In fact, it's just covariance divided by two numbers. Specifically, it's covariance divided by the standard deviation of h times the standard deviation of m. Okay, but we'll come to that, don't worry about that now. Okay, so I want to try and make you understand why this is going to measure how positively correlated or negatively correlated the two are. So, what we can first do basically is we can consider another map here. We can map this R2 onto something else, and basically I want a new map which I'll just call, what should I call this map? F. F is a good name for a map, and F is going to take any ordered pair x and y in here. It's going to take it to x I should have put h and maybe little m instead of x and y to denote that it's this is the h axis and this is the m axis, and it's going to take it to h minus the expected value of the random variable big H, and it's going to take it to m minus the expected value of big M. Okay, so let me explain what I mean by that. So these two random variables up here, h and m, they have expected values. So there is an expected value for your height. I don't actually know what the mean height of the human population is. I assume it's about, is it 1.8 meters? No, that's 6 feet. No, that's not the mean height. 1.6, 1.7 will be about the average height of a human. But there is some expected value of height. To make it concrete, I will write that it's approximately 1.6, but we're just going to use the symbol expected value of h from now on. Similarly, there will be some average mass, which is probably around 70 kilograms maybe. The expected value of mass is approximately 70 kilograms. Obviously, it will depend on, well, no, it won't depend. I don't know what the expected value of mass is in the human population. That's probably the expected values for the Western world. I don't know what the whole population of the human race is. I should have looked it up prior, but it doesn't matter. We're just going to use the symbols E of H and E of M. I'm just putting those numbers there to make it more concrete. And basically, what I'm going to do is I'm going to shift all of these points. So if I draw this mapping, here is this H and M, and what I'm going to do is, let's say here is the expected value of H and the expected value of M. So these are just two constants. So this is a point up here, and basically what I'm going to do is I'm going to subtract this from any point. So I'm going to shift this point down to 0, and basically I'm going to shift every other point by that same vector. So this vector here, every point is going to be shifted by that vector. So the origin is going to go somewhere down here, off to here, and this point is going to come down and form the new origin. So you get some new axes here, which we'll call, what should I call these? H bar and M bar maybe. These are the standardized ones, where the mean, oh dear, sorry, you couldn't see that. So what I've now done is basically I've moved this this whole plane down, basically. I've moved everyone down. I've moved this point, the expected value of h and the expected value of m. It was up here, but it's now been moved to the origin, basically. So what I'm effectively doing is I'm saying, let's set up a new thing of axes over here and call them the h bar axis and the m bar axis. So that's how this new set of axes here is relating to this old set of axes. So what we had is a bunch of points on these axes, so they'll still be there. But now, on here, it means that we'll have them something like this now, like there. Okay? So we'll have them on either side. So we'll have them in this quadrant now, in this new coordinate space. We might even have a few over here as well. Okay. And what we are now taking, why did I do this? Because if you now view this random variable t, which was the thing we are taking the expected value of to calculate covariance, it is now a much simpler random variable of this. Because t is just going to be this random variable, let's say h bar times m bar. So you're just going to times each of these. If you take a point in here, you're just going to take its, let's say, little m bar value and little h bar value, and you'll just times them together. So there won't be any of this subtracting off the expected value of h on the expected value of m business. You'll just take them in what they are relative to this coordinate system, and you'll times them together to get your value of t. So that's simpler, basically. Okay, now if we view, so basically what we have here is we have all these points which have a probability ascribed to them, depending on how many people in the original abstract probability space were given those, had those measurements, basically. So we've got two new measurements, m bar and h bar, which are, instead of your mass and your height, they are your mass take away the average mass. They are how much you're above. Oh, sorry, no, it should be h bar m bar rather than. That's trivial, but it should be. So h bar m bar rather than m bar h bar. But these measurements are your height relative to the average height, so how much bigger or smaller you are than the average height, and this is how much bigger and smaller you are than the average mass. Okay, so every person in this original abstract probability space up here has an ascribed value for h bar and m bar, and basically we want to take the covariance of these two original random variables h and m is equal to the expected value of h bar times m bar. Okay, so what we want to do is, basically, if we want to calculate the expected value of this, we want to look at all the points which have a constant h bar m bar value, work out what the probability of getting all those points is, so sum up all the probabilities of the individual points to work out what the probability of getting that value of h bar m bar is, and then basically add all of that up for every possible value h bar m bar can take. So basically, remember the definition of the expected value. It's saying sum over every possible value h bar m bar can take. So sum over, let's say, every real number. So I'll just use x to denote every real number, times the probability that h bar m bar is equal to that real number. Okay, so if we take the equation that h bar m bar is equal to some fixed real number, then that tells us that little h bar times little m bar needs to be equal to this fixed number, which tells us that little m bar is equal to whatever that fixed real number is divided by h bar. So if we look at all the points which satisfy this equation, well, we know that equation very well from calculus. That's an equation that looks like this. That's the set of points, basically, in this plane, this h bar m bar plane, which satisfy that equation. If x is a positive value, so this is if x is greater than 0, and if x is less than 0, obviously it's a curve that looks like this. So this is if x is less than 0. So these curves here are the sets of all points in these the set of all points in the two-dimensional plane in R2, which have a constant value of h bar times m bar. So if we want to do this sum, we're going to sum over every possible real value. So we're going to go over every single one of these possible curves. So as x gets bigger, it's going to go out more like this and go down more like that. So these are the x getting bigger, and as x gets smaller, closer to 0 from the positive axis, it's going to go more in like that. And then suddenly, when you flip to negative, what it's going to do is come out like here, like that, and then as you get more negative, it will go out like that. So you'll go over every possible value of the plane doing this. And basically what we need to sum up is the probability that you are on any one of these curves. So what is the probability that M bar and H bar actually are on this curve? And basically what you're going to do is you're going to look at all these points, and if you take a curve, so let's take a value of x, so this is a value of x, and we take its curve, this is the M bar is equal to x over H bar curve, then you'll look for all the little points that are on this curve. So we've got one here basically. Here is a point that was on that curve, and have we got any more? There's a point as well. And basically you will work out, therefore you will say that the probability that you are on this curve is therefore the sum of the probabilities of those 2 points. We know how to work out the probability of those 2 points. You just have to look for which people in the original abstract probability space had those measurements, and basically you will then add up that value of x, which is a positive value. So the more terms, the more points you have on this graph that are in these first 2 quadrants, these 2 quadrants here, the bigger the probability will be that you are on these positive curves, i.e. the more positive this sum will be. And if you have more points in these quadrants here, these 2 quadrants here, so quadrant 2 and quadrant 4, then you'll get more, then the probability that you'll have the negative values of x will be greater. So basically this great big sum, this expected value, this covariance, is working out what's the probability basically that you have points in the first and third quadrants, which are the quadrants where if you're above the mean in height, then you're above the mean in mass, and if you're below the mean in mass, you're below the mean in height. So these are where if one is lower than the mean, then the other is lower than the mean. If one is greater than the mean, the other is greater than the mean, i.e. they are the quadrants which correspond to positive correlation. Then you'll get, basically, if you've got more points in those positively correlated quadrants, you'll get a more positive value of covariance when you sum this all up, because you'll have more, the probability that you'll be in the positive values of x will be greater than the negative values of x, whereas if you have more in these second and fourth quadrants, then they correspond to the negatively correlated quadrants, because if you're below the value of mass, below the average value of height, you're above the average value for mass, and if you're above the average value for height, you're below the average value of mass, which suggests negative correlation. If you've got more in those quadrants, then that implies that you are negatively correlated, and coinciding with that, you're going to get more, the probability that you've got these negative values of x will be greater if you've got more points in these 2 quadrants. So that hopefully has given you some intuition as to why this definition of covariance does indeed give us some sort of insight into whether the 2 random variables are positive or negatively correlated. Okay, so the final thing we're going to do in this video is work out an easier way of calculating correlation, covariance. We haven't got onto correlation yet. So if we take the covariance of 2 random variables and now just replace those random variables with x and y, we'll come back to height and mass, because when we're doing correlation, it'll be a nice it's a very nice way of viewing it. So covariance of x and y, where these are just 2 abstract random variables, that was defined to be equal to the expected value of x minus the expected value of x. So the amount by which you are greater than or less than the average value, y minus the expected value of y times y minus the expected value of y. So how much you're above or below the average value for whatever the random variable y is. And basically, if we just expand this product out using the distributive property, and then apply linearity, we'll get another formula. So if we multiply this out, we'll firstly get x times y, which is these 2. Then we'll get minus x times the expected value of y. Then we'll get minus y, let's say, the expected value of x. And then we'll get plus the expected value of x times the expected value of y. Okay. So now just some revision of linearity. This is equal to the expected value of xy, because we're just going to, the expected value of a sum of terms like this is just the sum of the expected values. So then we'll get plus the expected value of negative x, the expected value of y, plus the expected value of negative y, the expected value of x, and then we get plus the expected value of the expected value of x times the expected value of y. Okay, so firstly, the expected value, this we can't do anything with now, so that just stays as it is, so we'll just continue that term, the expected value of x times y. Okay, now the expected value of y and that negative sign, they are just constants, so they can be pulled out, so we'll get negative the expected value of y times what's left is the expected value of x. In here, the expected value of x and that negative sign are constants, so we'll pull them out, so minus the expected value of x times what's left is the expected value of y. And then here, we're taking the expected value of a constant. Now, the expected value of a constant is just that constant. So this is just plus the expected value of x times the expected value of y. But these three things are exactly the same thing, so just cancel one of them off. This cancels with this, and we therefore get that this is equal to the expected value of x times y minus the expected value of x times the expected value of y, which is very analogous to that formula that we have for variance of a single random variable. Okay, so that will do for this video.